Today in this video, we're going to be looking at one of the more important rules of differentiation in calculus, and it's known as the chain rule. And I will tell you right now that kind of the explanation of how it works is, like a lot of things, more complicated than actually using it. Hopefully you'll see that actually using it really is not that bad, but sometimes trying to explain it gets a little tough. So take this one. I want you to, maybe pause it and think about how would you start this particular process. You want to differentiate that right there. Well, one thing you could do, of course, you could take and square this. 2x plus 1 times 2x plus 1, and of course you'd end up with this. And the derivative of that, of course, we got 8x to the first plus 4, and of course that's a constant, so it doesn't have anything. So we can do that. That is something that's very doable at this point. But then how about this one? How would you take the derivative of that? And maybe another way to think of this is 2x plus 1 to the 1/2 power. Well, my guess is you're a little bit more stuck on maybe what to do there. You might have an idea. You might say, well, we could do the power rule there. And I would say, actually, it would sort of work, but not quite. Parts of it would probably be correct and parts of it wouldn't be. And it's the idea of here we have a function. This is a linear function. Think y equals mx plus b. We've got a linear function inside of a square root function. Now up here we had a linear function inside of a quadratic function. We had an inside function part, we had an outside function part. Here we have an inside function part and an outside function part. Sometimes we can simplify it and then take the derivative. I can't really simplify this. I can rewrite it, and you might be thinking, well, we just use the power rule. Yes and no. It could be started that way, but in fact we will have to use the power rule in doing what's called the chain rule, but it wouldn't be done because we couldn't simplify it. We can't actually simplify this one. And so we're going to take a look at, even before I show you the chain rule, situations where you can take derivatives without the chain rule and situations where you can't take without the chain rule. So take this. Yeah, we can do that. We can just apply the power rule. But here we have a function inside, there's a quadratic function inside of another function that happens to this case also be quadratic. It doesn't matter that it's the same, but it's a function inside of a function. And you're going to see that's the theme here. Here's a trigonometric function. We have a rule already for how to deal with that. Here's a trigonometric function that has a linear function inside. Okay, by multiplying that by 1, we actually get away with the fact that this is a 1 here and not using the chain rule. Technically, the chain rule has to be applied here, but it doesn't show up in the simple version of it. And you'll see why in a few minutes. But here, I'd have to use the chain rule. And I will say, out of this whole section with the chain rule, these are the ones that I have students trip up the most. They forget that this is a function inside of a function. There's just a linear function. Here is a linear function inside of a fourth degree function. So it's a function inside of a function. Trigonometric function with a quadratic function. And here again, you might argue, say, well, that's first degree there. Yes, it is. But again, if we actually apply the chain rule here, you'd see that we sort of get lucky that we don't have to do much with it. But not over here. Here we'll actually have to do something with that. So the chain rule has to do with composite functions. How do we take derivatives of functions inside of functions, which are, again, the math word there is composite, which you've worked with composite functions before. F composed of g of x, g composed of f of x. All of these on the right-hand side, those are situations where you've got a composite function. So that's when we have to use the chain rule, which composite functions kind of come up quite often in calculus. And so again, this is kind of a big one. The chain rule gets used a lot as we go through this. Well, I'm going to show you something here, and this might not be totally clear, and some of you will get this, some of you maybe won't. I got these three gears turning here, and hopefully you would agree that the rate of change between these two, so there's going to be some rate of change here. How many teeth are passing within a minute here, and how many teeth are passing in a minute here. There's, of course, the rate of change. It's just going to be the ratio. This is not necessarily a changing rate of change. This is just a rate of change. But that rate of change affects this rate of change. I've got a function, and it's just a ratio again of the teeth here. A function here that this one controls this one, but then a function here where this one controls that one. So I have a function inside of a function. Again, we're looking at a composite function situation here. And if I can say this makes such and such y turns, well, this is going to make such and such u number of turns. It'll be different than that one because it has a different number of teeth. And this will be x number of turns, which again would be different than either of those because it has a different number of teeth. I'm going to use some calculus terminology here and kind of just start showing you the terminology. Here, by the way, just little gear ratios. We know that y turns half as fast as u. This one has half of the teeth, so this one ends up turning half as fast as that one. This one turns twice as fast as that one. And u turns 3 times faster than this one. All right, anyways, I got a rate of change here. Change in y with respect to u is a half. Change in u with respect to x is 3 to 1. There's 3. So now, how would I get from here to here is really the question. And this is the idea of the chain rule here. And by the way, you don't need to write any of this stuff down. I'm trying to sort of give you a visual explanation of the chain rule. I know, though, that the rate of change here times the rate of change here should give me the rate of change between these two, because essentially these would cancel out. So the rate of change here times the rate of change there should give me an overall rate of change. And that's going to be kind of the premise of the chain rule. I'm going to have one rate of change times another rate of change. If there's anything you get out of this slide, remember what I just said. When we use the chain rule, we're going to end up taking one rate of change times another rate of change to give us the overall rate of change. Okay, so let me try and explain it again. This time I'm going to use the theorem. If we have some function y is equal to f of u, which, yes, I know that sounds very funny, but please get past that, is a differentiable function of u, and u is equal to g of x. Okay, so realize what we have, a function where u is the variable for f, and then where x is the variable for g. We have a function inside of a function, a composite function. Then, of course, we have this. We have f composed of g of x. You've seen this before when we talked about composite functions in pre-calc. It does have to be differentiable. As long as this is still differentiable, then the way we do it is this. To get the differential equation, we take the derivative dy with respect to u. So that would be the outside one. Okay? So this stuff here is going to get plugged in for the u. So this is getting plugged in here. When you talk about composite functions, you got a function going in for a function. This says, hey, you take the derivative of the outside times, and this is what I told you a minute ago, there'll be a multiplication, times the derivative of the inside. Okay, so the du with respect to x. This is the derivative of the outside, and this times the derivative of the inside. And what I just said verbally truly describes the chain rule. You take the derivative of the outside times the derivative of the inside. Now there's a lot of notations that I'm going to use here, and those are important to introduce. There's more than one thing going on. Just so you know, as your teacher, there's more than one thing going on here. I'm teaching you the chain rule. I'm also trying to teach you stuff about some notation, specifically these u's that are showing up, because we're going to use u stuff a lot in calculus. And so there's like this underlying reason why I'm using u's. But the basic idea is pretty straightforward. You take the derivative of the outside times the derivative of the inside. Here's another way to look at it. If I want the derivative of a composite function, I take the derivative of the outside part times the derivative of the inside part. And hopefully this will make more sense as we go here. Here's another way to look at it. And again, I'm only showing you this because I also am, like I said, two things going on here. Chain rule, and I'm trying to get you used to this U notation so that we can use it later on. The derivative is the derivative of the outside times the derivative of the inside. If U is what's on the inside, I need the derivative of what's on the inside. Okay, so I've got f prime of U times U prime. Okay, you can find the rate of change of the outside part times the rate of change of the inside. Okay, that's really what I've just been saying here, repeating it over and over again. Okay, so when you do this, part of the problem is figuring out, well, what's the outside and what's the inside? And this is where the U notation is sometimes helpful. I'm not introducing a new variable when I do this. Basically, there's a trick in mathematics that says if you make it look simpler, it will be simpler. And it's a really, really common trick. And so what's done a lot of times in mathematics, especially in calculus here, is we substitute this to make it look easier so that we can figure out what we're doing. So what I'm going to do here, if this was my original composite function, you might look at that and go, I don't see where it's composite. Yeah, it is a composite. I have a linear function inside of a rational function. So I do have a function inside of a function here. What I can do is to try and help myself make a plan is I can say, well, let's let the inside part is always the U. Okay, so I'm going to let the inside part be this. And then the outside part would look like this. So what I'm going to do is I'm going to take the derivative of the inside, and now that'll require a rule. This is an easy derivative to do. It's just going to be the power rule. And then I'll take the derivative of the outside, which might not be the same rule. In this case, we would have to use a different rule that deals with rational expressions. In fact, this particular rule, we haven't actually covered that one yet. It's a rule that's coming. There's ways around it. We could think of this as u to the negative 1, but that's beside the point. My point is, sometimes you have to use one rule for the inside part, but a different rule for the outside part. Take this one. You have to go, okay, what's inside of what? Well, this would be the inside part, so that's the u. So you would take the derivative of the u times the sine of u. Now again, the only purpose for the u here is it makes it simpler, less confusing. And at first you might say, well, I'm plenty confused. It'll get better. Basically, what the u is telling me to do is ignore the 2x for a minute and just take the derivative of sine. So I take the derivative of 2x, I take the derivative of sine 2x, and then I would multiply them together. So you, in your mind, are substituting with this u. You don't necessarily write it down. In the end, it's still a 2x there. You're just sort of trying to make it look easier so that you have an easier time focusing on what you need to do. Here we've got a quadratic inside of a square root. So this stuff here would be the u, and then I would take the derivative of that. I would also take the derivative, I'd have to think, hey, what's the rule for taking derivatives of square roots? In fact, we don't really have a rule. What we do is we typically, again, write that as a power and then use the power rule. So that's the technique we've used. So it might just be a separate technique, not necessarily a new rule. But it is two different things, and when I'm done, I multiply them together. Now, there will be no u in your answer. Again, this is a visual trick. This u still represents all of this stuff, but I'm temporarily ignoring all this stuff while I do this, because this is easy for me to do. That would be 1/2 times u to the negative 1/2. We've done those already in class. It's just that now when I'm done, I would substitute this stuff back in. Now that I've taken the derivative, I'd put my original stuff back in. So I would take the derivative of this times the derivative of what I end up with here. And that's the chain rule. This one here, I'm going to let you pause it. Once you pause it and think, what's the outside and what's the inside? All right, so the inside is the tangent x. The outside is the square function. So it's a quadratic on the outside. It's a trigonometric on the inside. All right, let's actually do some examples here instead of that was just for practicing thinking about it. Hopefully after a few examples you'll find this is actually really not that difficult to do. In fact, most of my students very quickly get past actually writing u down. They just do it in their head. They go, okay, well, it's the derivative of the inside times the derivative of the outside. The outside part sometimes is a little confused, so I will write it down. So agree that the inside part is the quadratic part, the outside part is the cubic part. So I've got u is that. I'll need to take the derivative of that, which is the u prime. I'll need to take whatever that is, which in this case, of course, that's just 2x. So there's my derivative of the inside part. Now, the derivative of the outside. Instead of having it be x squared plus 1, I'm going to temporarily write this, because if I write it like this and say take the derivative, every Calc 1 student at this point should know, oh, that's just going to be bring the 3 down, reduced by 2. Which is exactly all it is. Easy to do when it's written like that, because again, if I make it look easier, it is easier. It's just that there's not going to be a u in your answer. You still got to go back and substitute this back in for the u. Okay, so again, it was a temporary trick just to make it look easy while you were dealing with the derivative. So I take my u prime, there's that. And here I've already substituted this back in for u. So times the derivative of the outside. And there I've accomplished the chain rule. It's the derivative of the outside times the derivative of the inside. Now I still need to simplify this, and I will in a second here. But just give you a second here to wrap your head around it. You could have, and like you said, typically I get students who can do this pretty quick. If you can just ignore the inside and go, well, let's see, I'll take the 3 out in front and I'll reduce it by 1, so it'll be a 2. There you go. Times, what would be the derivative of the inside? Well, it'd just be 2x. There you go. That's all I'm doing. And again, the u, some students really don't like doing this. They'd rather, it's like, hey, I can just do this derivative of the outside times the derivative. Perfect. Great. Then you don't have to mess around with this. Other students, they need to isolate that outside part so they can figure out, hey, which rule am I going to be doing there? Because it's just too much to take in at one time. And so it's just an easy little trick. Well, let's just call this stuff here u for a second, and then how would you take the derivative of the outside? That's how that works. Okay, so here I'm just simplifying. I squared this, and of course I'll distribute my 3 and multiply by my 2x and put my like terms together. But like I said, at this point the chain rule is done. Now I'm just simplifying. Let's take a look at another one. And if it helps, maybe pause it and try it yourself. The derivative of the outside times the derivative of the inside. Okay, so this is the inside. So when I take the derivative of the outside, well, I'm going to think of it as like this, which the derivative of that would be 3u squared. Okay, so I'll take the derivative of the inside, that part, which then the derivative of that is going to be a 3 and then a negative 4x. So there's my inside. Again, the derivative of the outside is I'm going to think of it like this. So I just use the power rule. It's going to be 3u to the second. But of course, I will still put this back in. Okay, so that's still going to get substituted in for the u right there. Now we put it together. The derivative of the outside times the derivative of the inside. There, the chain rule's done. Now I just got to simplify it. So yeah, I'll square this. I'll distribute my 3, and when I'm done, I'll have to multiply by this. It's going to be kind of a big mess here, but you guys can handle that. And I went ahead and graphed it there. Here you can see that the blue is my differential equation, and it has a value there of 0, which the red is the original function. It's flat right there, so the derivative should have a value of 0. Again, you can sort of check these graphically when you look at what's happening with these here. Again, up here, the derivative was positive, and then it's 0 and then it's negative. And of course right there we're going from positive through 0 to negative. So yeah, I think this is good. Okay, so let's take a look at a trigonometric one. Here, the u is the 4x. That's the inside part. The sine is the outside part. Okay, so the derivative of sine is cosine. You do keep the 4x there, okay, because I kind of am trying to push you here. If you need, think of it, well, what would it be if it was the sine of just u? Well, it'd be cosine u would be the derivative, and the u is 4x, so the 4x stays, times, well, the derivative of the inside is just 4. Do not do this. Do not multiply that times 4. It's not going to be 16x. If you want to rearrange it, you can put the 4 in front, because it's 4 times all of this is what it is. Okay. All right. I actually think I gave these to you before, but I'm not sure. The secant, in fact, I know I did. We have the derivative of secant and the derivative of tangent. I'm just going to throw those out here because I'm going to use them in a second here. Okay. Here's my function. Y is equal to secant x squared. The inside and the outside. Okay, it's not secant squared of x. It's the secant of x squared. Okay, so we got to have the derivative of the outside is the secant, the inside is the x squared. So the derivative of x squared is 2x. And if it helps, if you're still struggling, think of it as the secant of u. Okay, secant of u is secant tangent. Secant tangent. But the u is x squared, so it's secant x squared, tangent x squared. This is the derivative of the outside. X squared is my u, that's my inside, there's my derivative of my inside. Typically we put this out in front, so that's all I'm doing right here. All right, why don't you pause it and give this one a try. Now here, the outside is the squaring. This is a quadratic on the outside with a trigonometric on the inside. So why don't you pause it and give that a try. Okay. I have put a note here. Here's another way to write it. So the u would be tangent x. But you got to have a rule for that. Okay, so the derivative of the outside is going to be, let's say the outside is going to be u squared. So the derivative of that's 2u. So it's going to be 2 times tangent x to the first times, well, if you look at your rules, the derivative for tangent is secant. Secant squared right there. Still going to be squared because that one was squared. And there you go. Okay, here's another one. Why don't you pause this one? This one's a quadratic on the outside, a linear on the inside. Okay, so the derivative of the outside, excuse me, I guess I've got the derivative of the inside here is going to be 3. And the derivative of the outside, we have to bring the 2 out in front and reduce by 1. So that'll be 1. But when we bring the 2 out in front, that's where I'm getting this 6. The 3 from the inside times the 2 that came from bringing it down gives me 6. And then we've got this. Okay. Again, here, I don't need the chain rule. Here, I do or I don't. If you want to take time to square it first, then you won't need the chain rule. But you can do it with chain rule. Actually, I've had a lot of students that said, well, it's easier just to use the chain rule. I agree. You can, with practice, get pretty good at this. It's the derivative of the outside. That's supposed to be a 2. Times the derivative of the inside, and I'm done. Instead of taking time to use FOIL and multiply and then use the derivative. So this one, don't need the chain rule. This one, I do need the chain rule because I've got an inside part. Do not need the chain rule. Do need the chain rule because it's a linear inside of a 4th degree. and so forth. I think you get probably the idea at this point. Let's look at some little more interesting problems. What if we've got combinations? Okay, so I want to find the differential equation for this guy right here. Actually, so this is f of x is what it is. Well, I have a x times a cubic, but that cubic has a linear inside of it. That means I got to use the product rule. Product rule again is the first thing times the derivative of the second plus the derivative of the first times the second. You can be a little sloppy here. I've mentioned that before. So I'm going to call this my first thing. I'm going to call this my second. When I take the derivative of the second, though, I've got an outside and an inside part, which means, okay, now I got to actually use the chain rule there. So it's going to look kind of like this. Well, I'm going to take it a little faster than what I'm showing here. Here, I'm going to jump to this part. First thing. Derivative of the second thing. Okay, in your mind, ignore this. Use the, let's do the outside. The 3 would come down and then be a 2. 3 has come down, that would be a 2. Times the derivative of the inside, which should just be 3. There it is. Okay, so that's the first. It's the first times the derivative of the second plus the derivative of the first. I'm going back to my original thing here. The derivative of the first thing would be just 1 times the second. There's my second. So it's first times derivative of the second, but there I had to use the chain rule, plus the derivative of the first times the second. There, I've got my differential equation. I do need to simplify it, but I've taken the derivative and I have my differential equation. So now I'm just simplifying. I brought this 3 over here to multiply. I'm going to go ahead and I'm going to square this. I'm going to cube that. I'm going to put together my commoners. Actually, I cheated here. I broke off one and combined them. But I'm still just simplifying with my algebra. If you need, you might want to pause and figure out what my steps were there. But I'm just simplifying. And there's lots of ways to go about this. Okay, we can do the same thing. Quotient rule. What if we have a quotient rule situation and we have a function inside of a function? Well, then we need to combine quotient rule with chain rule. Okay, so here I've got t squared over t cubed plus 2, all inside of this thing being squared. Okay, so the derivative of the outside, the 2 is going to come out front, and that's going to be reduced by 1. All this will still be there. So there's the 2, that's to the 1, times the derivative of the inside. So this is my derivative of the outside, times the derivative of the inside. Well, for that I need the quotient rule, which is, again, the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. Okay, so at this point I have my differential equation. I'm just going to simplify it some. Okay, so a little bit of work here, and just like the last one, I'm not going to go through step by step explaining all my simplifications. You guys can figure some of that out on your own. But I'm just multiplying stuff together here and simplifying. Okay, I'm going to throw one at you to try. So this one, you've got a fraction inside of a function, so you're going to have to involve the quotient rule for this one, along with the chain rule. So why don't you pause this and give it a try. Okay, the derivative of the outside, bring the 3 out in front, reduce by 2. So there's the derivative of the outside, times the derivative of the inside. For that I need the quotient rule. Bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. If you got this far, you did accomplish getting your differential equation. I don't know if you tried simplifying it more or not. I don't think I actually wrote out the simplification. Okay, let's get back to stuff that's kind of familiar. Finding the derivative at a given point. So I want to find the rate of change at the point 2, 3. Well, of course, I need a differential equation for that. And to get the differential equation for this, I will need to use the chain rule because I have a cubic function inside of a radical fifth degree index. So you probably want to think of this as 3x cubed plus 4x all to the 1/5 power. That'd be a fifth root. So the power comes out in front. This is the derivative of the outside and reduced by 1, which is going to give me negative 4/5. So this is my derivative of the outside. And then you look to the inside. Okay, so that'd be 9x squared plus 4 right there, derivative of the inside. And you could at this point actually, you wouldn't necessarily have to reduce if you don't want to. You can if you want, because the question in this one is to find the rate of change at a given point. So simplifying or not simplifying, that's kind of a personal preference. What do you want to do? I did rewrite it, but you don't have to. The point is I'm going to put in my 2. What's the x value that I'm trying to find my rate of change at? I plug in my 2 here, here, and here. Okay, and you may want to have just left it written like this, which is fine. You can do fractional exponents on your calculator. Okay, so I run that through and I end up with the rate of change at that point is 1/2. If the book goes on and asks then to find an equation for the tangent line at that point, you do your y minus y1 equals the slope times x minus x1, and you could go through that. I do want to show you this. On your graphing calculator, if you have a newer Texas Instruments, and this is only when you're trying to find at a specific point, you can actually put this in graphically. Oh, excuse me, not graphically. You can put this in your calculator. If you go under your math button and you scroll down, you're going to see a place that has this symbol, meaning, hey, I want to take the derivative. But this only works when you're evaluating at a specific x point, because it's going to ask you for this number. If you're just doing a general find a differential equation kind of thing, your calculator will do you no good. But if you're finding a differential equation and finding the rate of change at a particular x value, the calculator will actually do it for you. So just so you know that. Here, my calculator won't necessarily do this for you. I want to find the equation for a tangent line. So I got to write an equation at the given point. What you could do with your calculator is this. You could go ahead and put this in. When x is a 1, it'll tell you what the slope is there. And then you'd have your slope, and you've got your x1, you got your y1. So you could do it faster, but because we're practicing the chain rule, I'm going to show you the chain rule here. So the derivative of the outside, bring this down. It's going to be 2/3 times 9 minus x squared raised to the, when you reduce that by 1, you're going to get a negative 1/3. And then the derivative of the inside is going to be a negative, that just goes to 0. So negative 2x. Okay, so there's my differential equation. I could plug in my 1 now. If you want to simplify it, but it doesn't really matter if you do or don't. Plug in your 1, get your specific rate of change at that particular point. So I've got my slope now, negative 2/3. And again, if you want to pause it and try it on your calculator, it should work. You just have to tell you want the slope at 1. And then we're going to do the y minus y1 equals the slope times x minus x1. And if you want simplify that, distribute your negative 2/3. And add your 4 to the other side to get it in y equals mx plus b. And when I do that, there's my y equals mx plus b version of it. And you can see there's my tangent line at that point. We can even do second derivatives, and sometimes the chain rule is involved. So let's take a look at this. So we got take the derivative of the outside. This is going to come out in front. This will get reduced by 1. Times the derivative of the inside. And we end up with this right here. I will give you a hint. If you're taking a second derivative, you're going to want to simplify this as much as you can before you take that second one. So here I'm going to put the 2x together. This is 12 with the 2x, 24x. Okay, and now I could take the second derivative again here. And in fact, you might look at this and go, well, can't I just multiply these together with FOIL, square it, and do one thing at a time? And the answer is sure. There's more than one way to do these. I'm just showing you using the chain rule. Now I do have the product rule here, which you might now be thinking, well, yeah, it'd be a lot easier just to square this, distribute the 24x, and do one term at a time. You're probably right. It probably is the easier way to do it. But I'm trying to show you the rules today, so I'm going to use the chain rule. First times the derivative of the second, which requires me to use the chain rule. Put the 2 out in front. Here's my u to the first times the derivative of the inside plus derivative of the first thing times the second. Okay, so there's technically my differential equation. I am going to simplify it. Oops, let me go back to that real quick. So there's I'm going to stop here. I'm going to simplify there. You might actually see this in the back of the book. They might factor these x minus 2 expressions out. I didn't, but that would be something you could do. So you'd have x squared minus 2 times 96x squared plus 24. Now we only factored out one of these. Think of this as u squared. So there'd still be an x squared minus 2 there. So you might see that in the back of the book where they factor it out. But I didn't. I left it that way. Okay, that's the chain rule. Here's some problems to take a look at. Somebody's little sense of humor having to do with the chain rule and having babies. Have a good day.